High friction can create unwanted heat, deformation, and wear of mechanical components for space machines. We all know that lubrication is an effective way to reduce friction and extend their lifetime, finally leading to the reduction of the carbon footprint for the space industry. But in space, liquid lubricant like oil will boil off in the vacuum, and extremely low temperature will harden the grease. In that case, solid lubricant is a good choice. MOS2 is a commonly used solid lubricant in space, and we call it lamellar or layered material because it has this kind of atomically thin planes that are very strong, but the actual force between those planes is very weak. That means they can slide over each other really well. When adding it to some frictional components, let's say a bearing system, what happens to the contact region is, as the inner ring rotates, those planes separate the real contact surface and slide over each other with very low friction, so the inner ring can rotate pretty smoothly. What we are going to do is to produce a coating on the contact surface, not an entire MOS2 coating since it is easily worn away, but MOS2 containing copper matrix coating, which mainly consists of very resistant copper, but also has MOS2 inside. In that case, MOS2 can be replenished to the contact region all the time, even if part of the coating is worn away. That's why we also call it self-lubricating coating. The coating is fabricated using cold spray technology, which uses a high-pressure gas to spray the injected copper and MOS2 powders on a substrate, like this. The copper particles, shown as greasy spheres, can bond due to their ductile property, and the MOS2, shown as black particles, will be entrapped in the coating. The most important parameters we need to optimize include the shape and ratio of the powders, as well as the gas pressure. All those parameters can affect the coating's structure, like MOS2 content in the coating, which will affect the coating's mechanical properties, like hardness, which will finally affect their friction and wear performance. After knowing the relations between those three aspects, based on cold spray theories and experiments, we can design the coating we want. After trying many times, finally we got this coating with enough thickness, 30 to 40 volume percentage of MOS2 content, and uniform distribution of MOS2. We tested its friction performance and found that its coefficient of friction stays steady after around 40 minutes, and its steady coefficient of friction reduced around a half compared to the pure copper coating. In future, we want to produce some coatings with much lower friction, and hope they can help the spacecrafts work for a longer time and more efficiently. Thanks.